Hello, physicists. Welcome to week 3 of the continuous learning. We are going to work on circuits today. Hopefully, you have spent some time already working on the activity, the PhET simulation of circuits. So you've got some handle on kind of what's going on. Um, my intention with this video is just to kind of get some basic stuff laid out in some notes so that you're familiar with it and you feel comfortable using some terminology and things like that. So I've put a notes sheet up on Canvas, so feel free to print it out if you'd like. Again, you can use your regular paper, whatever, but I would encourage you to stay engaged with this as it's going. Okay. So the very first thing that you did in your PhET simulation was to build a circuit that made a light bulb light. So just to kind of pull all of that together, we're going to go ahead and draw what that circuit kind of looks like. So in the PhET simulation, you had perhaps a battery, and batteries often look like this. And then you took some wires, and the wires in the PhET simulation are all very straight, but generally when I'm drawing these kind of drawings of a circuit, mine are kind of curvy because usually in the lab, when we draw these, they're kind of just curvy wires. They're not straight. And then you may have put a light bulb. So I'm just going to kind of draw what this looks like. And then there was another wire that went like this. And this circuit resulted in that light lighting up, right? And so we've got that really nice, pretty drawing. But the reason that I wanted to bring this up is because I want to make sure that you know that not only can you draw a circuit like this, but there's also a very technical way to draw this circuit as well. When you go on to a college physics course or just any other advanced electronics course or anything like that, if you walk in drawing your circuits like that, they're going to look at you a little bit funny and say, "Oh, friend, let's teach you something." So I'm gonna teach you some things right now, just in case. So anyway, we're going to use all three of those basic elements, but we're going to draw them in a little bit more of a technical way. So the first one is the battery. And the battery, instead of drawing just a rectangle with the little knob at the top for the positive terminal, we're going to draw the battery like this. It's just going to be two lines. One is longer than the other. And just for completeness sake, I'm going to let you know that the long one is always the positive and the short one is always the negative. You don't have to have those marked. The next thing to know is that when you draw wires, instead of them being all curvy or like in the PhET, how they're kind of at funky angles, when we draw a circuit diagram, everything is going to be at nice right angles. And so any wire that you have is just a straight line that's just at a nice right angle. Wires obviously don't actually bend like that, but that's just how we draw them in a circuit diagram. And unlike our cute little light bulb that we drew in our circuit drawing, we're going to draw a light bulb. Generally, when I draw them, I just draw them as a circle with that little curly Q in the middle. The curly Q represents the filament. That's that really small wire through an incandescent light bulb. I know that a lot of the things we use now are LEDs and that sort of thing, but for our purposes, we're just going to go ahead and draw them like that. And then we're going to connect the rest of the circuit because, as I hope you learned in that PhET simulation, you've got to have a complete circuit, a complete loop in order for lights to turn on. So in this kind of situation, we've got a complete circuit, just like in the drawing. This is just the more technical definition. I did also want to show you the other circuit that you drew, which was the one with the resistor, and we'll get into what a resistor is in a little bit here. But so this is just the other version. So you've got your wire, and then your resistors, that kind of funny peanut-looking thing. And that's really what they do look like. They did a nice job in the PhET of describing what they look like. And they're usually pretty little, and they've got little bands on them to tell you how big the resistor is. So it looks something like that. And oops, I'm so used to drawing my wires as straight lines that I went ahead and did that there. There we go. There's a nice little funky wire. But again, then in the circuit diagram, the battery is going to be represented by that long and short line. Okay. And then we've got square wires. And a resistor in a circuit is kind of a fun thing to look like. It looks a little like a shout out to the Liberty Lightning Bolt. It's going to be like that. It just kind of goes zigzag back and forth. And then, of course, we're going to connect to both sides. And it doesn't have to be not at the end of those wires, but that's just how mine came out. All right, so those are just some basic circuit drawings. Now we're going to look more carefully at the three elements that we just talked about in those circuits. So the first of those elements was the battery. And the battery provides something special to the circuit. You've got to have some sort of battery or some sort of source of energy. Okay, so the battery provides energy to the um, to the charged particles that are moving around in that circuit. One other way we can look at that, we also sometimes use the word potential. You say, "Hey, I've heard of that before." Yeah, because we talked about potential energy. And really what a battery does is to lift up those charges so that they have a space to then they've got some energy to give off. And we'll get a little bit more into that in a little bit. The next piece that's really important in a circuit is to have a bulb or some sort of resistor, or the technical term kind of for all of those things is a load. And the that's a D there. It was kind of hard to see. Sorry about that. And the thing that the load provides is a means to dissipate the energy. It is for sure possible to build a circuit that looks just like this with a battery and a wire. If anybody's ever done that before. But then the wire, which is usually kind of innocuous, and we're going to get to that. That's our third thing in just a second. Um, Usually the wire just helps to provide that space. But if there's no other load, no other bulb or resistor or toaster or whatever attached to that circuit, then the wire itself actually gets really hot. So this is not recommended. Okay, that would be not safe. Okay. Which is why it's important that we have a bulb or a resistor or something um, attached to the circuit. And then the third element of a basic circuit is a wire or a few wires. And the wire, like in these circuit diagrams that we have there, provides a path for the charges to follow. So in a complete circuit and a complete loop, the wire is kind of the this is the way you go, right? From the battery. The battery gives it that energy and those charges move. They kind of move around that circle, okay? Um, Following that path. Okay, so now we're going to kind of keep cruising on from the basic circuit things to what that really gives us. Okay, so the battery is providing us, I just said, is providing us energy. Really, what it's providing in terms of kind of the technical term is voltage. And you may have heard that term before, and that's awesome if you have. If you haven't, well, we're going to go through what it is right now. Voltage is marked with the letter V. Kind of makes sense, right? Voltage V. Okay. And the definition for voltage can get really technical really fast. And I don't want to overwhelm you because for our purposes this year, it's not crucial that you have all of the bits and pieces kind of organized in your brain, but I just wanted to give you a kind of a basic definition of what this is. So voltage is, I'm going to say, the relative amount of energy per charge, okay, that electrons um, have at any 2 points on a circuit. The relative amount of energy that electrons have at any 2 points on a circuit. So there are a couple of things there that I put in parentheses because when I was trying to kind of clear up a definition um, and make it simple, I was realizing that I was kind of brushing a few things underneath the rug and I wanted to make sure they were there. It's basically giving the charges some energy, okay? And the units for voltage, they're pretty simple. Um, They are the volt, and it's also marked with a V. So there's a lot of nice consistency there in voltage in terms of what is going on. So you're giving some energy to the electrons, and that's what this voltage stuff is about. So let's go back over here to find out what the measurement is related to a bulb or a resistor or any kind of load. And again, that load is basically anything that you have connected to a circuit. So when you plug something in to an outlet, you're completing a circuit. And so it could be a lamp, it could be a fan, it could be a toaster, it could be whatever. Any of those things are um, the relevant measurement, I guess, is resistance. And resistance is marked with an R. Again, pretty logical. Okay. The resistance, like what is it? It's a material's tendency to resist or to restrict the flow of charge. Okay. A material's tendency to restrict the flow of charge. And the resistance of a load, again, a bulb or a resistor or whatever, is the material, based on the material it's made from. Okay. It's based on the size of that material and the shape of that material. So there are some pieces there, and there's materials engineers do a lot of interesting work trying to kind of calculate what materials resistance is, and there's a lot of really cool science that happens in there. Resistance is measured in ohms. It's OHM, named after a guy named Ohm, okay? And the letter that we use to represent the units of resistance is a capital omega. So welcome to a new Greek letter for you. Omega is the last letter of the Greek alphabet, and that's the capital version of it, okay? And, then we get to learn to write something new, which is fun. The final measurement that we use when we're talking about circuits, in addition to voltage and resistance, is current. And unlike voltage, which is marked with a V, and resistance that's marked with an R, current is marked with a capital I. I'm not sure why, but it is. Current's definition is that it is a flow of charge, okay, in a circuit per time. So the key here is that it's actually a rate of the flow. So it's how many charges are moving per second. And that is the SI unit for current breaks down to charge per second. Charge per second is known as an ampere, also named for another physicist. That's a kind of a big word, so often we'll just call it amps, ampere, amp, and it's marked with a capital A. Okay, so now you've got the three basics there. You've got your voltage, your resistance, and your current. This is one of those things that I love to have lots of conversations about, but again, we're kind of limited on time and resources. So I'm going to kind of condense now the analogy that we often use for voltage, resistance, and current. I stole some really cute pictures from this website here that I've cited that kind of help to make voltage, resistance, and current make a little more sense. So I'm going to start from current because I think that that's really where we need to go. Okay, so current is the result of what's going on with voltage and resistance. And current is basically, if you think about it in terms of water flow, so these are like little water tanks hooked to hoses. So kind of like, your water spigot that is maybe connected to your house, except that we're not really talking about a water spigot. It's more like a bucket with a hole in it and talking about how much water is flowing. So in our analogy, current is literally just the water output or the water flow through the hose. Okay. And it's important to know that if you have a more complex system, then you can have different current at different places. And we're going to get into that in our next video. Okay. If we think about it in terms of, again, that water analogy, I'm not sure that any of you have done this, but maybe you have, or maybe it's happened on accident. If you've ever been using a hose like to water your garden or something like that, you may have had a situation where it gets kinked, it gets bent, or maybe you're playing with your siblings or something, and somebody's, using the hose for whatever reason, and you might accidentally, or maybe not so accidentally, kink it yourself, right? By doing that, you're changing the size, right, of the tube or the thing that the water in this case is flowing through, and that's going to affect the rate, right? Okay, so in this case, if we cause the tube or the resistor, okay, because that's what's stopping the flow, if we change the size of that, then we're going to get a different current, right? So we have a smaller area in this case, and that smaller area leads to a more restricted flow. Similarly, if you unkink that hose, right, then you're going to have more of a free flow. If you have a really, really wide um, hose, then you're going to have even more current or even more flow through there. And to be very clear, this analogy is very, very simplified, and that's important to know. But it does kind of help get your head around to what's going on. So again, the water actually coming out of or moving through the hose is like your current. When you change the size of that hose or that tube, that's going to affect your resistance or your restriction of that water. The other thing that you need is for that water to have some energy so that it has a reason to go somewhere. If you just leave a hose with a bunch of water in it, it's just going to be sitting there. Just like if you take a piece of wire, there are electrons in that wire, but they're not moving anywhere. They don't have any reason, they don't have any energy telling them to move in a certain way. But if you take that bucket and you lift it up, if you lift up that bucket, well, then there's going to be some pressure, right, pushing down on that water to cause that flow. So in our analogy, we've got water pressure, okay, and that water pressure, the higher up that we lift it, the reservoir, the greater the flow. Okay, the bigger the battery you have. So you have a 1.5 volt battery, you have a 9 volt battery, you have a 12 volt battery. The bigger that battery is, the more energy it's giving to those electrons. Okay, so hopefully that analogy helps a little bit. If not, you can for sure look that up a little bit. We can talk about it if you have questions. And then the last little piece here are the units that we're going to measure each of these um, kind of things in. Okay, so when we're talking about, um, or what, sorry, not what we're measuring it in, that was the units, but what we measure it by, like what tool we use. So voltage is measured with a voltmeter. Okay, resistance is measured with an ohm meter. And current is measured not with a current meter, which is maybe what you might want it to say, but it's an ammeter. And this isn't something that we would assess you on or test you on, but it's more just so that you're aware of that and you've got those words if you need them. So in the first part of your activity, we had asked you to kind of find a relationship between these three things, between voltage, current, and resistance. So I just want to go through that real quick just to kind of make sure that we're feeling good. So one of the things that you had to figure out the relationship between was resistance and current. So if the resistance increases, hopefully you saw from that activity that the current goes down. The current is absolutely dependent on the resistance, okay? And we could say here that current is proportional to, well, if one goes up and the other goes down, then really it's an inverse proportion, so it's 1 over R. We can also say, or we can also determine a relationship between voltage and current. As the voltage goes up, so again, this is like lifting those electrons higher and higher, giving them more energy. The more energy you give them, the higher the current goes. So here we can say that current is proportional to voltage. So you've got two things that the current depends on. And the thing that's really important here, you guys, when you're kind of going through this idea, is that current is the result of having a voltage, right? Or energy given to charges and them moving through something that's got resistance. So those two pieces have to be there. Okay, so we can put these things together and we can say that the current is dependent on both the voltage and the resistance. One of them is a direct proportion, the other's inverse. And this right here is the rule that we'll say kind of governs most of basic circuits. Okay, and this rule here is Ohm's law. Okay, we're going to do a problem quick with Ohm's law just to kind of make sure that it's making sense. It's a pretty basic rule, right? Looks very similar to Newton's second law, but just to make sure, it's been a little while since we've done some calculations like this before, so we just want to make sure we've got it. All right, so this practice problem says the current in a certain resistor is 0.8 amps when it is connected to a 90-volt potential difference. So just a little note here, I didn't actually get this one changed, sorry about that. Potential difference is just a fancy way to say voltage. If you get stuck by something like that, you can absolutely look at the units. The units are V. That means that it is a voltage. So I'm going to go ahead and be a good kid and write down my guess method. So I've got the current, that's I, in my resistor is 0.8 amps. And I know that my voltage is 90 volts. It says show that, so that's being really kind, right? It's telling you what it should be, but show that the resistance is 112.5 ohms. So I'm just going to solve for resistance and hope that we get that, okay? The relationship we have is I equals V over R. And then we can solve that for R. So if we multiply by R on both sides, divide by I, we get R is equal to V over I. And we can plug our information in. So we've got 90 volts divided by 0.8 amps. And if you plug that into a calculator, you will indeed find 112.5 ohms. Okay, so pretty simple process, but it's an important one. So I just want to make sure that that's making sense. And then let's do part B. It says, what is the current in the same resistor if the operating potential difference is increased to 120 volts? So now, and this is the part that's kind of interesting. Remember I said that the current is dependent on the resistance and the voltage. So in this case, the resistance is the same. It's the same setup, the same resistor. So we've still got that 112.5 ohms. Okay. Now, instead of operating at 90 volts, every time those electrons go through the circuit, they're actually being lifted up even more. They're given more energy. The voltage is 120 volts. And the question says, what is the current? So I is equal to question. I equals V over R. That is our relationship from Ohm's law. We don't have to do any manipulation this time, do we? So we can just say that 120 volts divided by 112.5 ohms is equal to, I got 1.06 or 1.06, I think that's just repeating amps. I'm going to um, round that to 1.1 amps. And there you go. I'm going to record a separate video today with the next piece. So go ahead and jump onto that.